Hello everyone, welcome to ICAST 2022. I'm Shashank, a second year PhD student at the University of Southern California. Today I'll be presenting a work titled Point Cloud Attribute Compression via Chroma Subsampling. This work is done in collaboration with KDDI Research. After briefly explaining about the background of point cloud compression and motivation, I'll explain about our contribution along with experiments and results. Point clouds are a set of 3D data points in space along with their attributes representing their object or a scene. Nowadays, point clouds are extensively used in immersive media technologies such as extended reality, augmented reality, and also used in remote sensing and autonomous driving. So in order for the point clouds to be stored and transmitted effectively, both their geometry as in XYZ coordinates and their attributes should be compressed. In our work, we mainly focus on compression of color attributes of the point clouds. The main motivation behind our work is in image encoding, the chroma components are encoded at a much lower resolution compared to the luma components. So this is because the luma channel contains much more sensitive information compared to the chroma channels. So because of this, most of the video encoders, including the most recent versatile video encoder, uses chroma subsampling. Also, these perceptual observations are valid for point cloud color attributes. As we can see in this picture, the luma channel contains a much more finer details about the attributes compared to chroma channels, which are relatively smooth. So MPEG currently has two standardizations for point cloud compression. First is video-based point cloud compression. In this method, the 3D points are projected to 2D planes and the existing video encoding methods are used. The other class of encoders are geometry-based point cloud compression encoders. In this, the encoders use the 3D geometry information to encode the associated attributes. As we can clearly see, the video-based point cloud compression methods, you can use the chroma subsampling, which has been developed for images and videos. But the geometry-based point cloud compression methods cannot use those cannot use chroma subsampling because there is no sampling and interpolation methods for 3D point clouds in 3D space. So if we have to look at the general pipeline of the GPCC, it is as follows. First, we develop a succinct representation of the geometry of the point cloud through an octree, and we use this octree to apply transform coding for attribute compression. So one thing to be noted here is point cloud attributes are converted from RGB space to YUV space, and the YUV components are compressed independently. In this current GPCC pipeline, there is no chroma subsampling block. So in our work, the main contribution is that we develop a computationally efficient 3D sampling and interpolation method, which can be used in GPCC encoders to achieve chroma subsampling. So here we encode U and V components independently and Y component independently, and U and V components are sampled before sending it to the GPCC encoder. So the chroma subsampling in images and videos are fairly straightforward. Since the pixels are arranged in a regular 2D grid, sampling is quite straightforward because we can choose every alternate pixel in horizontal and vertical direction. And even the interpolation is straightforward because we can use a nearest neighbor upsampling or bilinear interpolation. However, the main challenges in 3D point clouds are the points are irregularly placed in 3D space. And also there is a lack of spatial correlation, and the spatial point density also varies significantly. So because of these challenges, implementing the chroma subsampling directly from the images and video coding methods to 3D is not straightforward. So the main goal of our work is to design a computationally efficient sampling and interpolation techniques which is suitable for compression. So the existing graph signal sampling methods can be used for chroma subsampling, but they are very slow and also incurs high complexity overhead on encoders. So our main aim is to design a sampling method which can achieve different sampling rates and which are also computationally efficient. So the proposed sampling scheme is, first we create a sampling pattern on a regular 3D grid. So in a regular 3D grid, we generate a sampling pattern where we select every alternate points in X, Y, and Z direction. So once we have this sampling pattern, we intersect the sampling pattern with the point cloud, which can generate the point samples at a specific rate. So the mathematical formulation of our proposed sampling method is as follows. Let V be the set of points that if there are n number of points, and Fk is our sampling function, which maps each of these three-dimensional points to either 0 or 1, where 1 represents the sampling set. So the sampling criterion for each point is pretty straightforward. So we just take the sum of X, Y, and Z coordinates, and modulo of this sum should be equal to 0. If this is equal to modulo k of this sum should be equal to 0. So here k is the sampling parameter, and if we want to keep one out of 2 points, we need to set k as 2, which achieves 50% sampling rate. And this proposed sampling can be implemented with O of n operations. Since it is very efficient and implemented with a couple of bitwise operators, this won't incur much of a computational overhead in the complexity overhead in the encoder side. Similarly, we can use the sampling pattern for 33% sampling and for 25% and at 25% sampling rate. So the only thing is we need to tweak the sampling parameter k. So for 33% sampling rate, we need to choose every one out of 3 points in X, Y, and Z direction, and 1 out of 4 points in X, Y, and Z direction for 25% sampling rate. So once we compress the sampled chroma points, at the decoder end, we need to design a interpolation method where we have to interpolate the points from the reconstructed sampled points. So for that, we will construct a k nearest neighbor graph, and we interpolate the values based by averaging the attribute values of the neighboring reconstructed points. So this operation can be implemented with O of kn log n operations for graph construction and O of kn operation for filtering, which is graph filtering. So basically it's a matrix vector multiplication. So both sampling and interpolation methods are quite efficient. And let's see the experimental setup. So we evaluate the effectiveness of chroma subsampling on point cloud attribute compression on using 2 GPCC encoders. The first is a region adaptive hierarchical transform, and the other one is a region adaptive graph Fourier transform. We report the results of chroma subsampling at a sampling rate of 50%, and also we use RLGR encoder for entropy coding. Also, we test our methods on 8i full body data set. We set k is equal to 10 for KNN interpolation. To measure the distortion PSNR, we are using PSNR in both RGB space as well as in YUV space. For RGB space, we just take a pixel-wise MSE of R, G, and B components. But for in YUV space, we use a metric called color sensitive based combined PSNR, where the MSE of Y, U, and V channels are weighted based on certain experiments. So we use these two distortion PSNRs to calculate our to calculate our RD curves. So here are the results. For long-trace and red and black sequence, we observe a significant bitrate saving of around 10% and an average PSNR gain of 0.5 to 0.6. 0.5 to 0.6. These values are based on beyond Tegard metric. And for the other two point cloud sequences, we observe a very less bitrate saving, because these point clouds are inherently smooth and adding chroma subsampling wouldn't make much difference here. The same results can be seen in YUV space as well. Here we observed a bitrate saving of 14 to 18%, and a similar trend can be seen in RAGFT as well. An average PSNR gain of 0.8 to 0.5 is observed. So from these results, it can be concluded that the chroma subsampling significantly reduces the bitrate savings, bitrate to encode the point cloud at a similar quality on both the GPCC encoders. So here we do qualitative comparison of the reconstructed point clouds. So we construct the original point cloud with RAT and RAGFT without chroma subsampling, and we compare the reconstructed point clouds with chroma subsampling. As we can see, we could able to reconstruct the point cloud with little or no impact on perceptual quality using chroma subsampling, but at a much lesser bitrate. So furthermore, we also perform complexity analysis of our encoder and our chroma of sampling at the encoder end and interpolation at the decoder end. So for this, we compare the runtimes of RAT and RAGFT with and without chroma subsampling. So for this, we performed this experiment on first 20 point cloud frames of long dress sequence. And at the encoder side, we can see for both RAGFT and RAT, the sampling wouldn't add much of a complexity overhead. On the other hand, the interpolation will have a little more complexity on the decoder end. This is because interpolation involves construction of graph and also matrix vector multiplication. In conclusion, in this work, we have presented chroma subsampling for 3D point cloud attribute compression in GPCC encoders. We have proposed a novel and efficient sampling method for 3D point clouds at different sampling rates. So graph-based filters with KNN neighbor graphs are also used for interpolation. And we evaluated our method on 2 GPCC encoders. And the results are very promising, and we could able to reduce the bitrate significantly with little or no impact on perceived quality. So in our future work, we'll evaluate the proposed method at different sampling rates and also address the complexity of the interpolation techniques. These are the references. Thank you.